Hi, good evening all. This is Vishal Singhal from SalesStrat, your host for today. So we have uh, Mr. Tony McCaffrey. Uh, so he is an AI researcher and has developed a new model in which classic AI, ML, and humans all collaborate to counter each other's weaknesses and creative problem solving. As a cognitive psychologist, Tony studies all the human obstacles to creativity and devises counterintuitive techniques. So he will be taking us through this topic of AI, ML, human collaborative model, why and how, an interesting one. So I believe we have quite a few deep learning researchers as well as other PhDs and profs from across the world. So Tony, over to you. You can start the presentation. We are recording this session and will be made live in 2 to 3 days time in our on our StratSide YouTube channel. I will share the link for the same during the webinar. I request all of you to please ask as many questions as you uh, come across, and we will try to answer them all towards the end unless it is slide critical. Right, go ahead, Tony. Thank you.
Okay, thank you, Vishal. It's very good to be here. So I have a model of how classic AI and machine learning and humans can collaborate together in real time. And why would you want to do this? And how can you do this effectively? Okay. Oop. All right, so I'm going to start out with a bold hypothesis that this collaborative model of these three working together is always gives you better performance than any agent working alone, whether it's machine learning working alone or others. And I'm going to try to make that plausible with a very concrete example. And the contributing agents, the AI, ML, and humans, are countering each other's weaknesses. So they're leveraging each other's strengths and countering each other's weaknesses. And so that's how it becomes a better performer at the task. And the trick for this collaboration is to craft a friendly representation scheme, and that is both computer friendly and human friendly in its way of interacting with people and the other agents. So here's a little diagram of the three interacting with this structure that they share a very simple common language that they have to communicate with this structure. This is kind of goes back to the Blackboard model, the 1980s in AI. And it's a very visual structure of trees, which can be made very visual and intuitive for humans to work with. Now, it won't work. It will not only work with what we have today, but new approaches such as GPT-3, federated learning, GANs, they can become contributors to this collaborative model, and even future as of unknown AI approaches can also become a future collaborator of this model. So it's not limited to what exists today. So the basic mechanism is that examine the weaknesses of each contributor and devise ways for the other contributors to overcome those weaknesses. So we're getting close now to a concrete example. I'm going to dive into what this kind of common communication structure is that they're all contributing to and reading from. So it's both way. The arrows go both way. They're contributing to it and reading from it all simultaneously, as well as multiple humans. It's just for groups also, so multiple humans can also be contributing at the same time. Well, as I said, the trick to doing this is to craft this scheme, so let's dive in. Now, I'm going to use a rich task or activity, problem solving. So created a problem solving, and we're going to use causal graphs to represent it, and you'll see what those are in a minute. So here's our unique contribution to the type of causal graphs, where
Tony,
we're going to present
excuse
a
me, Tony.
goal. Yes.
There is a question. What is federated learning?
Oh, you want me to answer that now? I saw the question. Okay.
Oh, yeah.
Federated learning is a type of machine learning, specifically deep learning, in which the weights of all the going between the weights of the links between all the nodes and the layers, they are copied to another network. And so it's not just the data where they learn from, is that the links, the weights of the links themselves are copied over. And the hope is that it gets, you can do more analogous thinking and analogous problem solving that way. I know that's a bit vague, but I don't have the slides to kind of back it up beyond that.
Sure. Thanks.
Yep. All right. So the unique graph structure is a causal graph that has this structure where a person will put up a goal and then refine the goal into sub goals, and that upper graph will grow downward, and people will put the resources available to solve the problem at the bottom and break it up into their parts, and that those bottom graphs will grow upward, and then you interact the resources together and cause different effects. And when you connect the bottom and the top, then you've created a chain of interactions so that the main effect, the goal you want, has been solved. And this can be multiple connections can happen. So that's a bit theoretical, but that's a broad overview. Let's look at a concrete problem. Now, in the US, when we say football, we primarily mean this game with the oblong ball, and everybody's wearing helmets and pads and tackling each other and so forth. So I'm going to be referred to a problem in this game, a very violent game, is how do you reduce concussions? There's lots of concussions that occur from hits of helmets, hard tackles, head hitting the ground, things like this. So this is a tough problem, and my business partner and I worked on this using our brainstorming model. Jim Pearson is my business partner. And so let's put that goal at the top, reduce concussions in US football players. And at the bottom, we put the known resources we have to work with. And we have two types, the objects that we will consider and the energies. And the energies come from a standard list of energies that engineers are very familiar with. And there's a few more that I couldn't fit on my little diagram. And the objects, we could consider a lot of things, the cranium, the brain tissue, the neck, the parts of the helmet, but we'll just start with the two helmets that are colliding. So we have populated our resources at the bottom. We placed our goal at the top. And the first thing is that humans are very weak in this. I'm a cognitive psychologist, so I've studied human weaknesses in problem solving. And humans very much get fixated on the goal. So when you say reduce concussions and you ask people to, what's a different way to phrase that? They can come up with very few, actually, just maybe a handful. So this is where a computer can come along. It doesn't have to be a sophisticated AI program. It can just be a simple synonym explosion that looks things up in a nice thesaurus. And we came upon, when we worked in this, maybe 24 different ways to phrase this. I put a few up on the top: lessen impact and redirect energy and repel force and change the material, and all these different possible avenues to explore. So this is one place where the computer can easily counter a human weakness called fixating on the way the goal is phrased. So let's move ahead. Another way is that you want to be innovative when you work on this problem. It's been thought about a lot. It's been worked on a lot. And so we've grayed out certain things that have been greatly looked at, highly looked at. And how do we know which ones were looked at and which ones have been overlooked and which ones need exploration? So here's another human weakness that occurs is domain knowledge about concussions and all the previous research in concussions. So that might be a weakness for the people who are trying to give a fresh approach to solving this problem. And again, you don't need a fancy AI program to work on it. You just need a search engine, your Google, your Bing, whatever. And you can do the following series of searches to see which has been explored a lot and mentioned a lot in the search engine. So the first one, lessen impact, in the context of concussions, we created a search term, concussions lessen impact, will give you a tremendous amount of hits. And so we know that people have thought about this possible pathway a lot. So you can take all the different ways of phrasing the goal and run it through a search engine in the context of concussions and see which ones gives you a lot of hits and see which ones give you very few hits. Here's an example. When we first did this, there was repel force in the context of concussions, came back with some extraordinarily low number, like 6 or something hits. And so we kept it on the list as a viable solution path because we want to be innovative. We don't want to explore where everybody else has explored. We want to be innovative and go where people have overlooked. So there's another way in which a very simple use of a search engine can help you prioritize the rare approaches from the very common approaches to a problem. Now, the next thing was when my business partner, Jim Pearson, saw this on the graph, immediately associated repel with magnetism. And so this is where the human came in and came along, and there's a picture of him in cartoon form from a comic strip I put him in. And he made the connection between magnetic energy and repel force by the association of repel and magnetism. Because the two poles of a magnet are trying to get close to each other, they repel each other. Now, this is a weakness in machine learning, deep learning specifically, where machine learning, is very good at finding correlations, but currently it is very weak at finding causation. And just between two things co-occur does not mean that one causes the other. There's causal link between them. So machine language could not help us at this stage, and we needed good old human knowledge to help us fill in this causal link. But that will change because the machine learning is going to be learning on these causal graphs, and later on it will be able to make this causal association between repel and magnetism. So what we came up with, thanks to Jim's insight, this little diagram, is that if we magnetize the helmets of all the players on the field with the same pole, then when the helmets got close to each other, we'd have to fine tune the strength. They would drastically slow down and they would try not to hit each other. And doing tests in the lab under little models, most of the time the two helmets would change direction and there'd be a glancing blow instead of a head-on collision. So we went to the US Patent Office, explored going that direction, but found that someone had submitted this idea for a patent about 2 weeks, 3 weeks maybe, before we did. But it's still a good story of how our process led Jim to this great insight, and we were just a little bit slow on the trigger of finding it. Now, machine learning in this case is not going to be, it's going to be learning from these causal graphs, hundreds and tens of thousands and eventually millions of these causal graphs. So the machine learning that will be running in the background will gradually get better and better at making these connections. And because there's all the graphs are causal, when machine learning finds a correlation, it's likely to be causal, but such as magnetism and repel force. But that can always be double checked by the humans and the classic AI that is always running to check machine learning and check its work. So how does this come in handy? Well, it comes in very handy. Suppose you want to prevent collisions, cars bumping into each other, small little accidents in the parking lots of stores and theaters and so forth. Now, this is an analogous problem to the previous one, reducing concussions, only it's with cars instead of players wearing helmets. So the objects are now cars. All these energies are the same that engineers have to work with. And there'll be a few of the synonym, lessen impact and redirect energy and so forth. Few of those will be different. I did not indicate that, but a lot of them will overlap from reduced concussions. So we have this analogous problem that is very similar. And suppose our machine learning program has come along and has learned from many of these. And now the machine learning program can make the connection between repelling force and the use of magnetic materials. So that's how the machine learning will start out not contributing very much until we get a lot of experience and a lot of these causal graphs formed, but that'll become the data upon which machine learning will learn. So I have another question. That is an empirical question. Whether wearing magnetic helmets will affect the health of the head, specifically the brain. Now, we have to decide upon the magnetic intensity. And people go into MRI machines where there's an incredible number, I can't remember the exact calculation, and they have no effect on them. And this will be a much weaker magnetic field. So it is very promising when we have talked to physicists about this actually working and not causing long-term health issues with cognitive abilities, because the magnetic field will be so much less than someone actually does experience when they're in an MRI machine for a long time, for several hours, couple hours maybe. Okay, another weakness that is well known in machine learning is called the black box problem. And basically is that machine learning program will come up with a solution and it will not be able to present any reasoning by which it reached that conclusion and solution. And so a lot of people are working on this problem to make machine learning more transparent and understandable and things like this. But in this method, our fix is on this way of embodying things is that machine learning will come back with a very what's called a micro contribution, and it's not giving a bold conclusion with no reasoning. It is simply placing either a node or a link on this causal graph, and it's such a small contribution that people can look at it easily and say, oh, that's insightful, or oh, that is nonsensical. The machine learning program really messed up. Or wait a minute, I thought that was nonsensical, but that's really brilliant. And if you make the micro contributions small enough, the context allows the humans who are observing this to make a judgment whether this is a wild mistake of nonsense or it's a really insightful contribution that makes perfect sense to help solve the problem. So that's the way we deal with the black box problem. And it's not unlike how AlphaGo from the company DeepMind dealt with the problem and playing the classic game Go, that when Go just returns a single move, and I would call that small advance or small contribution, a micro contribution. And in the context of the game, this single move, players can generally determine quickly, wow, that was a very good move, that was a bad move, or they say, wow, that is a wild move, and it may take them several other moves to figure out whether it was a brilliant move or whether it was really a really bad strategy move. So we're using some of the same constraints here, where micro contributions make the black box problem, they minimize it because of the context of how it's being used. So back to our causal graphs that are growing upward and growing downward. Let's do a brief review. I've brought in weaknesses of each, the weaknesses of the humans contributing, weaknesses of machine language. I haven't talked about weaknesses of classic AI yet, but let's get into that. Two great sources that really give a very level-headed and critique with no hype, just telling what these programs can do and what they cannot do, are two books that came out last year in 2019 by people that you probably recognize their names. Gary Marcus is a psychologist who's steeped in critiquing current AI and coming up with alternative models to help us build an AI that we can trust, along with his colleague on this book, Ernest Davis. And then Melanie Mitchell, who has been in AI since the mid-'80s. She worked with Douglas Hofstadter at Indiana University. She gives a very level-headed, clear, concise critique of where we are actually at in AI, and forget all the hype you read in the media, excuse me, forget all the exaggerations that lead to mistrust. Here's a clear-eyed assessment of where we're at. So they were a source for a lot of, they're very good sources for reading about the current state of AI and machine learning, if you want to learn about where we really are at in the field. Another question came up. So I don't know. I just put the prevent car collisions, not at high speed collisions. I just in parking lots as people bump into each other. I don't know what approach is used in self-driving cars. I don't particularly think that they're using, turning on and off magnetic fields to keep the cars away from each other. It's probably just my guess. I'd have to research it. My guess would be they're just noting the exact location of your car and the next car over, and maintaining that distance and braking hard or accelerating accordingly to get away from that other car. That would be my guess. Okay, so classic AI weaknesses and the fixes humans' vast knowledge about. So to counteract this weakness in classic AI. So ever since the 80s, there used to be the buzz was expert systems, and they sit down with experts in mining or medical diagnosis and get the expert to do as many rules and rules of thumb and to articulate their reasoning. And they found that that was never sufficient to get a high performance out of the AI machines that would try to predict where mining would be rich and pay off, or medical diagnosis to become as good as a doctor in medical diagnosis. So one of the leaders from the Doug Lennett from the 80s decided to take on this challenge of humans seeming to have more common sense and computers having, being far from that, tried to make this, get people over decades to write down the explicit rules of all the things and facts of all the things we know that we would call common sense. And they've assembled millions of these rules, and they're nowhere close to having a machine, act and reason as we, a human, would be able to in a common sense manner. The other classic weakness is closed systems such as a game where there's only a few features that are relevant to the task of the game, the position on the board, and there's only a few features that are relevant that they have to worry about. Whereas you get out in open systems where a robot or a machine is trying to reason about the real world, and such as a driving car, that we're not so good at assessing all the possible scenarios and features. So whereas classic AI and machine learning can achieve superhuman performance in a closed system such as a game, as of now, in real world open systems, we're not so much. And self-driving cars are definitely at the forefront of this, and there's lots of debates and ethics, and are they good enough to be out on the road? So related to this in my work, in 2017, along with Lee Spector, another computer scientist, we were able to mathematically prove that in a real world open system, the number of features and scenarios of what could become relevant That list is not computably enumerable, so no computer can compute and or maintain or process a list like that. It can't list it out. It can't consider all these possible features that could become relevant. And so that's a big problem. There's a mathematical limit to how much a computer can know and reason about the world. So I'll show you that paper. Here it is. So the features of an open system are not computably enumerable, and the debate is not on the proof itself, but does that severely limit what a machine by itself can do? So that's the current debate in that area, based on a proof that I did with Lee Spector. Now, weaknesses in machine learning. So again, machine learning is known to be great at detecting correlations. That's its whole deal, its whole process, what co-occurs with each other. But just because two things co-occur does not mean one causes the other. Then the black box cannot easily get inside the reasoning of a machine learning program to figure out why it came to this conclusion, and the closed system. So the things to counteract this are causal graphs that deal exclusively with causation, so that a machine learning program coming to correlations in a causal graph and learning based on millions of causal graphs that it has in its data might be more likely to come up with causal conclusions. And micro contributions, so that's a very small step, so people can verify and get inside the black box is not so dark, and can see its reasoning. Oh, that was a great move. Oh, that was a great placement of that node and connecting those two things, or it was not. And then the closed system versus real world system, once again, relying on human knowledge to fill in a lot of the background knowledge and common sense that seem to elude and may forever elude our approaches to represent the world. Now, human weaknesses. So we've talked about classic AI weaknesses. Now we're at the third partner, machine learning weaknesses, now human weaknesses. Now this is one of my areas of expertise. I wrote a book all about how to overcome any obstacle to problem solving and creativity. And it lists out all these obstacles, cognitive, human, mental obstacles and weaknesses that humans have. And I've only talked about in detail goal fixation and how to counteract that by machine. And goal fixation, as you remember, is just fixate on the way the goal is phrased, and you're unable to rephrase it in many different ways. Maybe you can only rephrase it in 4 or 5, 6 ways, whereas using a thesaurus, you can explode into probably, dozens of different ways of phrasing the goal and refining the goal. And it helps humans break out of this fixation that they can get into. These are other human weaknesses, and I have functional fixedness, analogy blindness, and on. And I have other techniques that a machine can do to guide a human to get unstuck in all these different ways that we know about. In fact, every different way we know about that humans get stuck, I have a counteracting algorithm where a machine can help the human get unstuck. So those are the weaknesses for AI, that a broad overview for machine learning and for humans. And this is, my degree in cognitive psychology. This is my area of research in cognitive psychology. Now, we're just summing up here, and then I'll open it up for more questions. So this goes back to initial graph at the beginning, where we have all these current and older classic AI, machine learning, individual humans, human groups, very current things, GPT-3, GANs, federated learning, which deals with the weights on the graphs, on the layers and the links. And they're all contributing and reading from this common causal graph structure. And we call this brain swarming. And we call this brain swarming because it's a play on brainstorming, which evidence doesn't work very well when humans get together as far as creating new, more ideas or better quality ideas than if you worked alone for a while, maybe 30 minutes, and then came to the table and shared your ideas and built upon them. So it's based on we call it brain swarming. It's also, the swarm in there is very intentional in the name because it's based on a few principles from how insects solve problems together. So let's see. I might give a little bit about that. We have a good amount of time, and we're doing well on time. So let's see, I have a couple slides on how swarm intelligence, insights from insects come along and influence how we piece all this together for all these agents to interact together. But first, the next slide was that not only are the causal graphs very structured, where the goal grows downward, the resources break into their features, grow upward, the interactions among the resources produce effects, and hopefully we get closer and closer to achieving the goal until the top graph and the bottom graphs connect at least once. And they might connect in many places. And if that happens, then you have multiple solutions, and then you can start to analyze the pros and cons, the benefits, the costs of each solution. And not only is the graph highly structured, but the grammar underlying it is very structured. So everything up on the top starts with a verb, an action verb like reduce concussions or prevent collisions or lessen impact or repel force. And so everything that you want to have happen, you need an action verb to express the change you want to occur. Or in some cases, you want no change to occur, and so you'll use the verb maintain. Maintain something, maintain this stability, or maintain this pressure. So, but they all start with a verb. All the resources at the bottom and their features are either nouns, noun phrases, objects, energies, helmets, cars, magnetism, and on, or they're adjectives, they're features. It's tall, it's wide, and you can get more precise on how tall, how wide, so forth. So there's a very structured grammar for creative problem solving, as well as a very structured graph in which it goes on. And we tried to make this so it's both computer friendly, bunch of trees in the graph, and a very regular grammar to express it, but also human friendly, where these phrases are intuitive. This is the way I would say the goal. I need to reduce concussions in football players. I need to prevent collisions. I need to do this. And so computer and human friendly together as far as human friendly, the graph is a bunch of trees, and it's my test. I use it with my students. They can very intuitively read the graph and add to the graph at the right place. So now, so brainstorming is our name for this causal graph structure plus its grammar to address creative problem solving in this manner. And not only are human agents contributing, multiple human agents, but AI, machine learning, and other types of AI can certainly be contributors who read the graph structure and contribute to it. Now, I'll just jump ahead a little bit to, and this will be the last thing, and then I'll go back to the final slide. Stigmergy is part of swarm intelligence, where biologists and now computer scientists have studied how insects specifically communicate and solve problems with each other. So Stigmergy is a very specific way where they leave traces in the environment that influence the other agents in the environment. So they use the external environment to leave traces. And a concrete example is in ants. And I primarily think of how ants have influenced how we put together our graph structure. So very briefly, excuse me, the ants are coming out of the nest to look for food. They wander, they meander, and in B, the lower ant, who had the more direct path, reaches the food first. Now, as in C, the green line means that as the ant returns to the nest, it starts dropping a chemical, a pheromone, to kind of mark its trail of where food was successfully found. And when it gets back to the nest, then all the other ants that are coming out of the nest can detect this pheromone, this trace in the environment, and they will follow that chemical pathway to the food, because they know it's successful. Food is at the end of this pathway. Now, since the lower ant completed the pathway back to the nest first, the new ants coming out of the nest, they will follow its path, and more will follow its path, as opposed to the longer path, which took longer to get back to the nest. So finally, in the final one, basically all the ants are following this very successful path. Then it turns out to be a shorter path than the upper path to the food. So we took this idea, and in our brainstorming graph, instead of leaving chemical traces, we are leaving traces of ideas, parts of ideas. Here's a feature of an object. I'm going to place it here on the graph. Here's an effect when these two resources interact. I'm going to place it here on the graph. Here's a refinement of the goal, and I'm going to replace it here on the graph. And so we're leaving traces of things on the graph so that other agents, whether they're machine or human, can come along, read it, and contribute to it. So if you want to find out more, here's a link to published articles on this type of approach to creative problem solving. The Harvard Business Review has made some very nice videos on brainstorming and using humans, and how it's much better than brainstorming. And there's a 1-minute video capturing that. And there's my email address, and there's my LinkedIn. contact line, and I will leave it at that. So thank you very much for allowing me to present this alternative model, which boldly I would say can always be better, will always be better performer than classic AI by itself, machine learning by itself, or whatever it comes along, because every approach, including humans, has their set of weaknesses, and we can craft and refine the multiple approaches, whether machine or human, to counteract the weaknesses and make a better performer for the task. So thank you very much. And thank you, Vishal, for this opportunity.
Great. Thank you, Tony. It was very interesting insights. I especially like the two helmets theory, as well as the relation you gave it to like autonomous cars to the question that was asked. So thank you for that. And now some questions, if anybody wants to ask, please do that. So I've already posted the link for the Self-Study YouTube channel, where this will be posted in a day or two.
Okay, I'll make sure I get that link too.
So people are appreciating. It was very nice session, very wonderfully explained. There are some computer scientists on this, as well as people from Germany, US, India. This is the first time, I think, or second time in last 2 years we have done webinars on such an early time, and pleased to see that a lot of people were able to make it. So look forward to more sessions from Tony, and thank you all for joining.
All right.
Have a great
Thank
day.
you for the opportunity again.
Welcome.